All right, today we're going to demystify a true powerhouse in the world of data science, principal component analysis, or PCA for short. It's a super powerful technique for finding the hidden story in your data, even when it's buried in a ton of noise. So let's jump right in.
I mean, just think about it. You've got a data set with hundreds, maybe even thousands of columns. It can feel completely overwhelming. So how on earth are you supposed to find the real story in all that noise? Well, that's the exact problem PCA was built to solve.
So, the whole reason PCA even exists is to tackle something data scientists called the curse of dimensionality. Now, that sounds pretty dramatic, but it's really just a fancy term for a simple idea. Sometimes more data or more features isn't better. In fact, it can make things way, way worse.
And this flood of dimensions, it causes some major headaches. Our computers start to chug. We can't really visualize the data to see what's going on anymore. And our machine learning models might even start paying attention to random noise instead of the actual signal. Basically, it just gets impossible to figure out what's really going on.
So, how do we fight this curse? This is where PCA gets really, really cool. Instead of getting bogged down in all the numbers, let's think about it visually, geometrically. PCA is all about finding a better angle, a much more insightful perspective to view our data from.
Imagine your data points are like a big, long, skinny cloud floating in space. Now, your original axes, the columns in your spreadsheet, they might not line up with that cloud at all. It's like looking at it from a weird, unhelpful angle. What PCA does is it literally rotates the whole thing so that a brand new axis runs straight down the longest part of that cloud. That new axis, that's where all the action is. It captures the most variation, the most information.
And that new axis, the super informative one, yeah, that's our principal component. And here's the key. It's not one of your original columns. It's a new thing, a cleverly calculated mix of all your old variables, specifically designed to be as descriptive as humanly possible. The very first principal component is the biggest, most important story your data has to tell.
All right, so we get the what. We know what PCA is trying to do. But what about the how? How does it actually pull this off and find these powerful new components? Let's peek under the hood, but don't worry, we're going to skip the super heavy math and stick to the core ideas.
Okay, so this is the single most important idea to get. PCA basically makes one big assumption. It says variance equals information. So wherever your data is most spread out, that's where PCA thinks the most interesting action is happening. Those directions where the data's all bunched up and has low variance, it sees those as less important, maybe even just noise.
The whole process can really be broken down into three main steps. First, you center the data, just to make sure we're focused only on the variation. Next, you calculate something called a covariance matrix. And all that is this really neat grid that shows you how your variables move together. Like when one goes up, does another one tend to go up, down, or just stay put? Then finally, using that map of relationships, we can pull out our new principal component.
Now you're going to hear two nerdy words thrown around a lot here: eigenvector and eigenvalue. I know, they sound super intimidating, but the concepts are actually pretty simple. Think of the eigenvector as just the direction, a signpost. It points the way for the principal component. And the eigenvalue, that's just a score. It's a single number that tells you how much information, how much variance is packed into that direction. A big eigenvalue means a big story. Simple as that. So, we found our new components, we've ranked them using those eigenvalues. Now comes the fun part. We get to decide to keep only the most important ones and just toss the rest. This is where the real magic happens. It's called dimensionality reduction.
And honestly, the results can be just staggering. It's really common to find that just your first 2 or 3 principal components can capture something like 95% of the total variance from a data set that might have started with dozens and dozens of variables. I mean, think about that. You get pretty much the whole story, but with just a tiny fraction of the original complexity. That's a huge win. Just look at this chart for a second. Our first component, PC1, it captures a whopping 75% of
everything going on in the data. Then PC2 comes along and grabs another 20%. So together, just those two give us 95% of the entire picture. All the other dimensions combined, they only account for that last 5%. They're basically just static, background noise.
Now, of course, there's a catch. There's always a catch, right? When we toss out those smaller components, we are technically losing a little bit of information. But here's the thing. PCA lets us make this a really smart, calculated trade-off. We're consciously choosing to lose a tiny bit of detail to get a massive win in simplicity and clarity.
Okay, before you get all excited and start running PCA on every data set you can find, we got to talk about the rules of the game. It's an amazing tool, but it's not a magic wand. It has certain rules and assumptions we have to respect if we want to get results that actually mean something. Okay, one of the first and biggest things you got to watch out for is scale. If your variables are measured in totally different units, say height in meters and weight in kilograms, the variable with the bigger numbers is going to totally dominate the analysis, and that's not what we want. So what's the fix? You standardize your data first. And that's basically what using a correlation matrix does for you. It puts everything on a level playing field so you can make a fair comparison. And you also need to know about a few core assumptions that are kind of baked right into the math. PCA is designed to find linear or straight-line relationships. It assumes that the biggest variance is the most important signal, not just random noise. And by its very nature, the components it creates are uncorrelated with each other. If your data breaks these rules, well, PCA might not give you the answers you're looking for.
All right, let's bring it all home and put PCA in perspective. At the end of the day, it's a phenomenal tool for exploring your data, for simplifying it, and for really understanding its fundamental structure.
There's a line from our source material that just nails it. PCA reveals the intrinsic structure of data. It's not making anything up. It's just giving you a better lens, a new coordinate system that's perfectly lined up with the story your data has been trying to tell you all along.
So by squashing down all those dimensions while keeping the really important stuff, PCA turns what was overwhelming complexity into something you can actually understand and gain insight from. It's a foundational skill for anyone working with data. So I guess the real question for you is, now that you have this powerful tool in your back pocket, what hidden patterns will you uncover first?